Hey there! Today you're going to learn a bit about the amazing world of quantum physics, and we'll see how it led to a new kind of computer, quantum computers. We'll go over the following questions. 1. What are quantum entanglement and superposition? 2. How does a qubit work? 3. How are qubits made and kept stable? 4. How are quantum computers and algorithms built? 5. How do we read the results and see them on a regular computer? 1. Quantum entanglement and superposition. In the quantum world, particles act very differently from what we're used to. Superposition. A qubit can be both 0 and 1 at the same time until we measure it. Entanglement. Two particles are linked so that measuring one instantly sets the state of the other, no matter how far apart they are. A classic example, the double-slit experiment and delayed choice. A photon acts like a wave until we measure it, and like a particle when we measure it. If the decision to observe is made after the photon passes the slits, the results still adjust to the observer's choice. Conclusion. In the quantum world, information and observation shape reality. Practical uses. Quantum cryptography. Secure communication where any interference breaks the entanglement and is detected. Quantum sensors. Super precise measurements. Basic research. Studying the nature of time, space, and consciousness. 2. The qubit, the core of a quantum computer. A qubit is the quantum version of a bit. In a regular computer, a bit is 0 or 1. A qubit is 0, 1, or a superposition of 0 and 1 at the same time. Qubit properties. 1. Superposition, parallel calculations. 2. Entanglement, connection with other qubits. 3. Interference, strengthening the right answer and weakening the wrong one. 3. How qubits are made and kept stable. Types of qubits. 1. Superconductors. IBM, Google. Tiny current loops at about 0.015 K. Microwave pulses put the qubit into superposition and perform gates. 2. Ion traps. IonQ, Honeywell. A single ion is held by electromagnetic fields and lasers. A laser moves the ion between states vertical bar 0 and vertical bar 1, creating superpositions and entanglement. 3. Photonic qubits. Xanadu, PsiQuantum. A photon with a specific polarization or path in an optical setup. The source creates a photon already in the vertical bar 0 state, and gates put it into superposition. 4. Topological qubits. Microsoft in development, based on exotic quasi-particles, Majorana fermions. They promise more stable operation, keeping qubits stable. Ion trap, vacuum plus electromagnetic fields plus lasers. Atom floats in empty space. Optical tweezers, a laser pit holds a neutral atom. Goal, to avoid noise and accidental collisions with other particles. 4. How a quantum computer works. 1. Initializing qubits. All qubits are set to the vertical bar 0 state. Superconductors are cooled, ions are reset to their ground state with lasers, photonic qubits are created with the right polarization. 2. Quantum gates, Hadamard, H, superposition. C0, entanglement, phase gates, ST, changing the phase of the wave function. 3. Evolution qubits are in superposition and calculate all options in parallel. 4. Measurement, the qubit collapses to 0 or 1. Algorithms are designed so that the correct answer has the highest probability. Main algorithms, Shor's algorithm, factoring numbers, Grover's algorithm, searching in an unordered database, quantum modeling, molecules, materials, reactions, quantum ML algorithms, experimental. 5. Reading and displaying information, qubit signal, photon current, detectors, analog to digital conversion. A classical computer processes the results, displays them on screen. We repeat measurements many times, build statistics, determine the correct result. In summary, a quantum computer is a new processor that solves problems faster for some algorithms. All control, reading, and display still happen on regular computers, laptops, and servers. Basically, a quantum computer right now is like an accelerator, similar to a GPU for graphics, but for specific calculations. Conclusion: quantum mechanics opens up a new way of looking at reality. Information and observation shape the outcome. Qubits allow us to use superposition and entanglement for calculations that classical computers can't do. Modern quantum computers already exist, and even though they are still experimental, they are already giving us an edge in modeling, cryptography, and optimization. The future of quantum technologies promises a revolution in science, engineering, and understanding the universe.